Alright, so the notes we were taking in class somehow got corroded, so we're going to start all over again. And we're going to be talking about proving theorems, which comes out of lesson 2-3. And I apologize, I'm in the classroom and the air is running, so that might be that noise you hear in the background. Alright, let's talk about theorem 2-1. And midpoint theorem. Should be capital, sorry. Now again, this is a theorem that has a name, so if we were ever to use it in a proof, we could just call it the midpoint theorem. So it states if M is the midpoint of segment AB, M being a point, then the length of AB, the length of AM is equal to 1/2 the length of AB, and the length of MB is also equal to 1/2 the length of AB. And so basically what we have is a segment AB, and then we've got in the middle M is a midpoint, and basically it's saying the small section here, A of AM, is going to be equal to 1/2 of the whole section AB. Okay, and that's what this theorem says. So how do we prove this theorem? So when we're proving a theorem, we can't use it in our theorem, otherwise we wouldn't be proving. So I'm going to go to the next page. And what we do is we take the hypothesis of that theorem, and that becomes what we are given to use in our proof. And we've got that M is a midpoint, and I like to use abbreviations, so that's my abbreviation for midpoint, of segment AB. And we're going to prove the conclusion of that theorem, which would be the measure of AM is equal to 1/2 the measure of AB, and the measure of MB is equal to 1/2 the measure of AB. Now with all proofs that we're going to do, they're going to provide us a diagram. So we've got, again, A, B, and in between M. Okay? So remember, when you're doing a proof, you got to think of what is the big idea here. What are we actually studying? And right now what we're looking at is we're looking at segments. So the only things that we can use in this proof have to do with segments. So we've got segment addition postulate, we have understanding what a midpoint is, and so on and so forth. So we've got all these things that we could use, but we can only deal with ideas that deal with either segments or mathematical properties. Okay? And so we'll start with a given. And in our two-column proof, we have statements on the left and the corresponding reason on the right. So we start with M is the midpoint of segment AB, and the reason we can write that is it's given. So one of the things that I'm always doing is I'm always going to look at what information I got from my statement that I could use for my next step. And the only interesting thing out of M is the midpoint of segment AB is that idea of midpoint. So generally speaking, the key idea in a statement becomes a reason for the subsequent step. So keep that in mind. So next, let's see what we know. What is a midpoint? Well, according to our definition, a midpoint is the point that divides the segment into two congruent parts. So it's vitally important that you know your vocabulary from class. Well, what are the two parts? Well, it says segment AM is congruent to segment MB. And that would be definition of a midpoint. So we don't write it out, we just give the reference to how we're able to make that statement. Now, I'm going to tell you that the next step I do is a separate step. The book tends to do it as a combined step, which is actually wrong, so we have to be cautious with that. If you look at what it is that we're trying to prove, we've got the measure of AM, the measure of AB, the measure of MB, the measure of AB, and we've got equals. But right now, I have a congruent symbol. So what we need to do is somehow take that congruent statement into equality. Oops, sorry, that should be blue, I mean black. All right, so we have the definition of congruence that says if two objects are congruent, their measures are equal. And it's a biconditional because we can say if we have two lengths that are equal, then those objects are congruent. So this would just be the definition of congruence. And I like to use the congruent symbol when I abbreviate. Okay, great. So now somehow I have to involve AB. So I'm looking at my diagram, and I'm seeing that I've got AM, and I'm seeing that I've got AB, and I'm seeing that I have MB, and I need to come up with some way to relate those together. Okay, so again our goal is to get AM equals 1/2 AB, MB equals 1/2 AB. So somehow I've got to involve the AM, the MB, the AB, and that's where segment addition postulate. Oops, sorry about that. That's where segment addition postulate comes in. So in segment addition postulate, it says the measure of the small segment, AM, plus the measure of the small segment, MB, is equal to the measure of the larger segment. That's your segment addition postulate. All right, so somehow I can't have two different little guys. I need to have two of the same little guys so that I can get that 1/2 on the other side with the AB. So if you notice step 3, it says that we've got the measure of AM is equal to the measure of MB. So what we could do is a little substitution either here or here. So I'm going to just do it with one of them. And we're going to go ahead and substitute in AM for MB, because I'm going to do the first one that shows. Oh, sorry. And I just wrote the same thing over again. Try that again. So that is substitution. Now, some people may call that transitive, but really I use substitution property of equality when you're replacing a piece of an equation. When you're replacing an entire side, now we're talking about transitive property of equality. So then, how many AMs do we have? We have 2. And some kids want to tell me this is addition property of equality, but the problem with that is you would be adding the same thing to both sides. I'm not adding AM to the left and AM to the right. I'm only combining like terms. Combining like terms, remember, is really the distributive property of equality. So again, my goal, I'm always focusing back on my goal, and my goal is to get AM by itself and the number on the other side with the AB. So we have a couple of options when we do that. We can either multiply both sides by 1/2 or divide both sides by 2. Okay, I like to do multiplication property of equality because that justifies getting the 1/2. So remember with geometry in our proofs, we show the result of doing the math. So AM equals 1/2 AB, and we give the justification on the other side where we get multiplication property of equality. Now again, I'm not going to be hard-pressed if you say division property of equality in that same step. So we've gotten half of our goal. We've got the first one done, check. And now we need the second one. Well, if you go back to step 3 and we know that the measure of AM and the measure of MB are the same, I can just use substitution again. And I'm going to substitute in for AM the MB, and I get MB equals 1/2 AB. And that's going to be substitution property of equality. You could also call that transitive property of equality, and that's okay as well. So either of those. So now we've got both of what we need, check, check, and we've done our proof. All right, so let's deal with this another theorem, and let's focus in on the angles. We've been doing this, have you noticed? We've talked about segments, and then we talk about angles. We talk about segments, we talk about angles. So this theorem is 2-2, and it's angle bisector theorem. So it's like the midpoint theorem. It looks very similar, but we're dealing with our angles. So the hypothesis is if ray BX is the bisector of angle ABC, then, here comes the conclusion, the measure of angle ABX is equal to 1/2 the measure of angle ABC, and the measure of angle XBC is equal to 1/2 the measure of angle ABC. Okay, so again, a picture. And again, you have to trust what it says, not what it looks like. Sorry for the phone call. So we've got angle ABC, ray BX. And so basically what it's saying is that this small angle, angle ABX, is going to be equal to half of the big angle when it's a bisector. Okay, so let's go through that proof. And basically the proof we're going to do is mirroring the one we just did, except for now we're going to use anything that talks about angles. So the given is the hypothesis. And the hypothesis was that BX, ray BX, is the bisector of angle ABC. And what we're going to try to prove is the conclusion that the measure of angle ABX is equal to 1/2 the measure of angle ABC. And then we're going to also prove that the measure of angle XBC is equal to, half the measure of angle ABC. So again, the diagram, it's just kind of a repeat of what we had. We have A, B, C, and X. Okay. So we have a statement, we have reasons. So we start with a given that ray BX is the bisector of angle ABC. So take note of my abbreviations. And again, we look for the key word. Ray doesn't help me, angle doesn't help me, but the word bisector, that's the key word. So that idea is going to show up as my reason for doing the next step. So what do I know about bisectors of angles? I know that they give you two congruent angles. So what are the two congruent angles? We would get, and we're going to keep orientation the same. So the ABC is on one side, the ABX, so on and so forth on the left. And we're going to keep the letters in the same orientation as what we were given. So if you notice here, we've got angle ABX and angle XBC. So that's the same order that we're going to be writing ours. So we've got angle ABX is congruent to angle XBC. If you look at that definition, it says nothing about that measures are equal. So that's the definition, and you can't say bisector. It's of an angle bisector. Very important that you distinguish between the two. We've got a segment bisector and we've got an angle bisector, and you need to make sure which one's which. But if you notice again, we're trying to prove things that deal with equality and deal with measures. So we're going to take the statement from 2 and turn it into measures. So we get the measure of angle ABX is equal to the measure of angle XBC. And that, again, is our definition of congruence. So we're just going to keep following the kind of pattern we had before. And last time what we needed to do is involve that measure of angle ABC. To do that, we're going to use angle addition postulate. So measure of angle ABX plus measure of angle XBC is equal to the measure of angle ABC. That's your angle addition postulate. And then we're going to do exactly the same thing. I need to get 2 of the same angle so that I can divide both sides by 2 or multiply both sides by 1/2. And so I get the 1/2 on the other side. So we're going to use step 3 to do some substitution into step 4. And it doesn't matter which direction we go. I'm going to start with the ABX showing up twice by substituting in that the measure of angle XBC is the same as the measure of angle ABX, because that's the first one that was mentioned. Alright, the measure of angle ABX plus the measure of angle ABX equals the measure of angle ABC. And all we did was replace one piece of that equation with a piece of information, so that's really what substitution property is. And now we can use the distributive property to combine like terms, and we get 2 measures of angle ABX equals the measure of angle ABC. And so that's our distributive property. And then we can do the multiplication property of equality. Multiply both sides by 1/2, and we get the measure of angle ABX is equal to 1/2 the measure of angle ABC. And again, if you call this division property, I don't mind. And then that's the first one, and to get the second one, we're going to take the statement 3, where we had some equality going on. So we're going to take the measure of angle XBC and substitute it in for the measure of angle ABX. Just substitution. You could call that transitive because you're replacing an entire side with an entire side. Okay. Alright, so we've got another proof just to share with you, trying to get you in the mode of how to do proofs. So this one doesn't come from that proving those theorems, but it's going to utilize one of those theorems, and hopefully you'll be able to figure that out pretty quickly. Oh, sorry. So to prove, no, sorry, given, I'll get it. We've got ray EG bisects, or is the bisector, of angle DEF. We also have that ray SW is the bisector of angle RST. And I'm going to tell you that the measure of angle DEG is equal to the measure of angle RSW. And then we're going to prove that the measure of angle DEF equals the measure of angle RST. So we got 2 diagrams. We've got DEF. we've got ray EG, we've got angle RST, we've got ray SW, and then the last is the measure of angle G is equal to the measure of angle DEG, excuse me. Okay, so we've got bisectors, and we know that bisectors can create congruent angles. So it sounds like we may be using that definition again. So given is that you can write all the given at one time, or you can also split the given up, so deal with one given at a time, and then add, once you've done everything you can with that given, add in the next given and continue on. So I'm going to demonstrate that in this proof. So what I can conclude from the bisector is that angle DE, actually, I can use, because I know I have an angle bisector, I can actually use the angle bisector theorem. I'm not using it right now. I mean, I'm not trying to prove it, so I can use it. And so I can say that the measure of angle DEG is equal to 1/2 the measure of angle DEF. I can also say that the measure of angle RSW is equal to 1/2 the measure of angle RST. Now, what that allowed me to do is to bring in what I need in my conclusion. Okay. Oh, yeah. I think I put that in the wrong spot. I need to erase that purple one. Let's see. I'm going to go back. Okay, let's try that again. So DF and DF, angle DF, and then angle RST and angle RST. And since we know from the third given, that the measure of angle DEG is equal to the measure of angle RSW, which is right here. Okay? So let's... Okay. So the reason that I get to state that is the angle bisector theorem. So this is an example of using that theorem. All right, so now I'm going to bring in that other given, because right now in my proof I don't know that the measure of angle DEG is equal to the measure of angle RSW. So that's another given. So again, I can do all the givens at one time or split them up like this. So then that allows me, if I have two things that are equal, then I can substitute in what they want. And remember what I need: DEF on the left, RST on the right. So if I'm going to go to step 3, and I'm going to replace the information from step 2. So again, I'll underline DEG, and this is the same as DEG. Okay. So we replace measure of angle DEG with 1/2. Oops, sorry. One-half the measure of angle DEF, that's the same as the measure of angle DEG, is going to be equal to the replacement for the measure of angle RSW. Remember, is going to be RSW, okay, and then that 1/2 is going to go in here. So we get 1/2 the measure of angle RST. So again, you could call this substitution, you could call it transitive property, but of equality. And then I don't want the halves there, so if I multiply both sides by 2, that gives me measure of angle DEF is equal to the measure of angle RST, which is exactly what we needed, and so that was multiplication property of equality. Okay, and that's that proof then. Pretty simple. All right, I've got a one vocab word, and then we're done here, and that is deductive reasoning. And when we use deductive reasoning, we are proving statements by reasoning. So something that we are reasoning out, we're just not saying just 'cause. From accepted postulates, which all postulates are accepted, right? Well, they can't be made up postulates. That's basically what they're saying. Definitions, theorems, and given information. So all of these key pieces of information are what we use to, one step at a time, get to our answer. And given information also includes the diagram. Okay? All right, good luck tonight.